Good afternoon and welcome to today's presentation, Electrical Equipment Failures, Cause and Liability. In today's webinar, Mr. Abend will discuss supply and distribution, equipment reliability, failure analysis, statutes, and documents. To give you a little background about our presenter, Robert Abend, he is a state-registered electrical engineer. He has an extensive background managing engineering hardware and software design activities. Mr. Abend also has experience directing manufacturing operations, primarily in the areas of integrated circuit development, test, burn-in, water probe, data processing, and computer network design. He developed several manufacturing facilities, including power and grounding systems. Mr. Abend is also experienced in the implementation of modern manufacturing quality control methods and has years of experience with forensics analysis. Attendees will require a passcode. The word for today is electric. During the Q&A session, we will ask that you enter this passcode into the Q&A widget for CLE reporting purposes. The Q&A is located to the left of your screen. Please remember that if you are applying for CLE credit, you must log onto your computer as yourself and stay for the full 60 minutes. You are also required to complete the survey at the end of the program. Tomorrow morning, we will send out an email with a link to the archive recording of the webinar. The slides can be downloaded from the resource list to the left of your screen. Thank you all for attending today, and Robert, the presentation is now turned over to you.
Okay, thanks, Emily. My name is Bob Abend, and I also want to thank everybody for attending today. What we'll be talking about is electrical equipment failures, what causes those failures, and how to identify liable parties. So we'll go through a brief introduction. I'll go through some important definitions that are needed for this presentation, and they're tailored to that. I'll talk about a manufacturer's supply and distribution processes, the definition of equipment reliability, how to conduct failure analysis when an equipment failure occurs, some important statutes and documents, and then we'll summarize. So I think we all understand that equipment failures can result in damages, explosions, fires, injuries, and deaths, and result in some form of litigation. So what I'll be going through and explaining in this presentation is why equipment failures happen, how to identify the liable parties for the failure, the definition of equipment reliability, some failure analysis methods that can be used. I'll point out some valuable references that can be used when you're involved in a case. And a couple of notes on the presentation is that although this is slated primarily to electrical systems, it applies in part to mechanical systems and certainly to electromechanical systems as well. And there'll be some math presented. If you don't understand the math, don't let it concern you. It's primarily there as an objective base for some of the conclusions that I'll reach. So as far as my background as it's related to this presentation, Emily mentioned that I'm a registered electrical engineer. I ran an engineering design team in the development of the Delta and Atlas rockets that are currently used to launch U.S. payloads into space. I recently left the Air Force as Director of Engineering on the Space-Based Infrared Systems Program, a satellite surveillance activity. Spent a lot of years in component engineering, primarily in the microelectronics industry, in identifying reliability issues and solving them. And I've spent quite a number of years, both part-time and full-time, as an expert conducting forensic analysis in these areas. So, some definitions for the purposes of this presentation. A system is the end product that's delivered to the end user. It's a top-level assembly of subassemblies and components. A subassembly within the system is an assemblage of components that perform a function within the system. As an example, you might have a digital display on a refrigerator that was a subassembly within the refrigerator system. Component, again, for the purposes of this presentation, is the lowest level system element. It could be a nut, a bolt, a wire, transistor, microcircuit, etc. Reliability, and we'll talk more about the formula for reliability, but it's a function of time, and it's the probability that a product will operate correctly for a specified period of time. It's always a number between 0 and 1. 0 probability obviously indicates no chance of survival, and a 1 indicates a 100% chance of survival. Again, you won't ever see 0 or 1. It's usually a decimal number between those two values. Failure rate, given by the Greek letter lambda, is the number of failures for a product that are likely to occur during a specified period of time. You'll frequently see units in failures per million hours, but there are other measures as well. Euler's number is simply a constant. I have it rounded off here to 2.71828, and it's given by the lowercase letter e. Redundancy is an important method. It provides fail-safe backup in a system for safety-critical functions, and we'll talk more about redundancy. Failure analysis is simply a discipline that one employs to identify system failure root cause, and root cause has a specific definition that I'll talk about. So, there are a lot of factors that can drive product safety and reliability. How well the system or product is manufactured is important. The quality control and associated inspections during manufacturing are very important. Of critical importance is the system design. If the design engineers don't design the system as a safe product, there's not too much that can be done to fix that. And you can see quite a number of other factors. These are certainly not all factors, but the bad news is that there really are a lot of factors that can degrade product safety and reliability. The good news is that there are subsequent factors that can correct the other deficient factors. As an example, let's take a case where an operator on a production line makes an error that creates a potential safety hazard in a product. That error can be caught and corrected in a subsequent inspection or test that's performed before the product is distributed. So that's the good news. And kind of associated with the bad news and good news is the fact that you'll find that most product hazards result from multiple deficiencies. In this case, an operator did something wrong. It wasn't caught in an inspection or a subsequent test, and there are usually others. Okay, the supply and distribution management conducted by the end product manufacturer is one of the more complex and critical sets of operations that are associated with an end product. And an end product manufacturer will receive assemblies and components from suppliers and sub-tier suppliers so that they can assemble and create the final product that goes out to the customer as an end product. To that end, it's important that the product manufacturer or importer provide the suppliers and sub-tier suppliers with a detailed set of specifications that ensure they meet the requirements of the overall system so that the end product goes out as a reliable and safe product. It's also a good idea for the end product manufacturer to conduct on-site supplier audits to physically go out and ensure that the suppliers and sub-tiers are doing what they're supposed to in terms of inspections and other activities. Once the product is produced, it goes into the distribution chain and typically would be distributed to dealers, end users, and supported by a field service organization. Now, the field service organization can be supported by or run by the end product manufacturer, the distributor, or the dealer. And it's of critical importance that the end product manufacturer provide necessary documentation, training, and that they certify and select the entities in the distribution chain very carefully. Having an unqualified, untrained field service organization, as an example, or dealer for that matter, is not good. An unqualified field service organization can create safety and reliability hazards on their own. And of course, this chart isn't the end-all, be-all. There are a lot of different variations that can exist. So, other manufacturer responsibilities. I talked about design, a safe design created by the engineering design team is very important. Like I said earlier, you can't really correct design deficiencies very easily unless the design has gone back and redesigned. Recalls. I think we've all seen recalls in the form of automobile issues where a manufacturer sends out a recall notice. To that end, each product that's sent out needs to be serialized. It needs to have a unique serial number so that it can be traceable to the distributor, to the dealer, and ultimately to the end user. Record retention is very important. If a production facility were to find that a test operation was done improperly and it resulted in safety defects in certain components that were produced over a given period of time, it's important that necessary documentation to identify the serial number of products affected is retained. Otherwise, everything would have to be recalled. Communication of recall notices to the end product user, the dealer, and the distributor is also very important. And corrective action, effective corrective action, I should say, is of critical importance. You'll find that problems occur, recalls occur, corrective action is not done properly, and it results in further recalls and further issues. And I'll talk more about how to conduct corrective action properly. So this graph is frequently called the bathtub curve. There are three phases that products typically go through: infant mortality, a constant failure rate or useful life phase, and a wear-out phase. On the vertical axis of this graph is failure rate, or lambda, that I described earlier. And on the horizontal axis is time. Infant mortality, products have initial defects that cause initial problems, but the failure rate decreases rapidly to a constant failure rate phase. And if a product is used long enough, it'll start wearing out, and you'll see the failure rate increase at a fairly rapid rate again. Some notes on the bathtub curve. The the product manufacturer is responsible to ensure that infant mortality failures are largely eliminated, particularly in safety-related areas. If you purchased an automobile and the dome light went out and the stereo system stopped working, that wouldn't be the end of the world, but you wouldn't want the brake system to fail or the steering system to fail. All my calculations throughout this presentation, including reliability, assume that we're in the constant failure rate phase. They don't apply to the infant mortality or wear out phase. So, what is reliability? It's given by the formula R of T, reliability as a function of time, is equal to E, Euler's constant, to the minus lambda times T exponent. And again, lambda's failure rate, time is equal to T, and Euler's number is 2.71828, and that's rounded off. So, if you think about it, this would be expected, but R of T is a negative going exponential curve decreasing with time. And the reason for that is that the reliability number for a product operating correctly for a month would typically be higher than that same product if you expected it to operate for a year. So the longer the time involved that you expect the product to operate properly, the less likelihood it's going to make it. And that makes sense. Okay, so what can a manufacturer do to ensure that infant mortality is eliminated before the product is distributed? Test and inspection points are very important during the production process, and this isn't often talked about, but the level at which those tests are performed is very important. So if you're testing the final product and you don't perform tests at the assembly level or component level, you may not have visibility into defects at the component level and assembly level. So key tests need to be conducted at the component level, the assembly level, and the final product level. And you don't, if you're performing an electrical test as an example, you may not have access to conduct that test at the component level in the final system. And the same thing is true for inspections. You may not be able to see a component in the final product. So another important tool that can be used by the manufacturer is burn-in. And burn-in is essentially operation of a product for a given period of time. And frequently it's stressed with perhaps a higher temperature than it would normally see, or a higher voltage than it might see. And the reason for that is you want to accelerate latent defects to show up as faults and eliminate them before they go out in the field. In burn-in, it's very important to select the stress level and the time period so that you don't degrade the overall life of the product. Errors in the burn-in process can do that. Along with burn-in are delta measurements, and they're kind of a handy tool as well. You can take a measurement before burn-in and take a measurement after burn-in, the same measurement. And if there's drift, you can put a limit on that drift so that if the voltage you measure before burn-in is significantly different after burn-in, it could predict or show a latent defect that's degrading over time that will later show up as a fault. So those before and after burn-in measurements with limits applied can predict future failures. So these are some of the tools that can be used. So here's a simplified reliability model. I've got a system with 3 components. They have a 0.98, 0.95, and 0.93 reliability level for 1 year. To calculate the system level reliability that those components feed, you multiply the reliability levels together, so it would be 0.98 times 0.95 times 0.93, and that's equal to 0.87, or an 87% chance of operating properly for 1 year. So 13% chance of failure in 1 year isn't particularly good, but this is just an example. So from this, you can, since it's a multiplicative hierarchy, you can see that more components equals more complexity and lower reliability. Redundancy is an exception, and I'll talk about that later. To give you an example of a more realistic system, if you had a 100-component system and each with a reliability of 0.99 or 99% operation for 1 year, you'd only have a 37% chance of that system working properly for a year. So that 0.99 seems like pretty good reliability, but it's not high enough. Components need to be really reliable. Okay, so here's an example of a redundant design method that can be used during the design phase by the engineers. And in this case, I have a primary component backed up by the very same component, a duplicate, both, of course, with 0.99% reliability for a year, and that's not good enough. So the failure probability is now 1% or 0.01 for 1 year. The probability of failure, and the way redundancy works is if the primary component fails, the duplicate component takes over and backs it up, and the system continues to operate properly without any problems. So if you want to calculate the reliability now that we've added redundancy, you subtract the reliability from 1 and square that for 2 components, and you end up with a reliability of 1 in 10,000 failure probability for 1 year, which isn't bad. Not great, but not bad. So if you would take this a step further and use triple redundancy with the same level of component reliability, you now improve the chance of proper operation for a year to 1 in a million. I'm sorry, chance of failure for 1 year to 1 in a million, which is starting to become pretty decent, particularly for a safety-related issue. So, what component reliability levels does a manufacturer have available to them? And there are quite a number more than I'll present here, but space level I talked about, probably one of the highest levels there are, because satellites need to operate properly for a number of years, and they're not easily repairable, as we know. Medical, if a pacemaker is implanted into an individual, failure of that device could result in death, so they're probably equal to or slightly less than space level. Standard military, aircraft grade, commercial, and at the bottom of the barrel is retail consumer. And typically those are lower level reliability components, except in safety critical functions. If an appliance or a product starts a fire, it can result in death. The components that are used to ensure safety-related reliability levels need to be up there, probably in the space to medical level. Just to diverge here for a minute, quite frequently when manufacturers address an issue with safety on a product, they find, to their surprise, that reliability and the reliability improvement resulting from the safety issue it drives lower field costs, better production yield, and to their surprise, and they find that their costs went down and they have a safer product. Kind of a nice benefit. So here's just another example, a little more complicated reliability model, hypothetical for a dishwasher. I put in three subassemblies, an LCD display, a water pump, and a water heater. And each of those subassemblies has two components driving it. So the reliability model ends up being the multiplication of the two components for each subassembly, and then you multiply the reliability levels for each subassembly to end up with the overall dishwasher reliability. So the LCD display and water pump, a failure in those subassemblies probably results in a technician coming in, and if they perform the repair properly, your system is back up and operational, and there's not a safety issue. The water heater is not in the same category. An electrical water heater in an appliance like this would be controlled by a temperature regulation circuit that turns the heater on and off continually to maintain the water within a certain temperature range. Well, if that temperature regulation circuit fails, the water heater can go into a meltdown mode and cause a fire. So as a fail-safe backup, thermal fuses can be used to sense the temperature of the water heater and shut it down if it reaches a specified temperature before it starts a fire. You probably want those thermal fuses to be redundant, perhaps have two of them, and it is a safety critical device. And here's why. If there's a temperature regulation failure and the heater goes into meltdown or over temperature, and if the thermal fuse fails to open the electrical circuit and shut down the heater, you can end up with a structure fire. Not a good result. Component reliability metrics. How do you know, or how does the manufacturer know how reliable a component is? Frequently when you purchase components, you get with it data sheets that describe the component specifications. And one of those specifications will typically be reliability or expected reliability. Not always, but usually. Military Handbook 217F is a fairly extensive reference for various types of electrical components. Unfortunately, it hasn't been maintained by the government since 1991. It's still a decent reference because improved manufacturing methods have improved the reliability of components since 1991. And if you use the numbers, the reliability numbers in that handbook, you'll usually be on the safe side. If you've been producing a product for a long time and there haven't been significant changes to the product, you can use that reliability data from past history to predict the reliability of future products if they're the same. I wanted to talk a little bit about software and firmware, since software adds another dimension to hazard prevention. And many products today with microprocessors and so forth employ firmware or software. And firmware is simply software that's burned into hardware. It's non-volatile, it's hard to erase, and so typically firmware would be more reliable than software. But the advantages of software is that it can monitor the hardware continually for faults and execute corrective action. You can run multiple identical parallel software paths and use voting methods to minimize errors and system failures. And of course, software can perform system self-tests prior to and during operation and they can shut down the system or flag the operator of the system to notify them that something's wrong. Okay, so I guess we're up to the question phase for the first half.
Okay, and could all the attendees please type the passcode into the Q&A? Our first question is everything that is being said apply to gas-powered equipment as well as to electrical equipment?
Gas-powered, in other words, gas engines?
So this person gave the example of a lawnmower.
Most of what's discussed here would apply to gas-powered lawnmowers, yes.
Okay, and in your experience, can all the entities on your supply and distribution diagram be liable?
I've not seen all of them be liable, but I believe they all could be. Certainly a supplier, the manufacturer, distributor, dealer, field service operation could all be liable for a system failure.
Okay, and have you ever seen a matter where no entity was liable?
No. In every case I've been involved in personally or have seen, there is always somebody liable. You know, there is the possibility of random failures during the useful life phase of a product, but I've never seen that ever be the case.
Okay, and does the third-party label provide assurance that the equipment is safe?
Third party being like UL or CE, or is that what it's?
I believe so, yes.
The question refers to. No. As I pointed out during the UL certification process, if I've gotten to that slide yet, I don't think I have I? I'll tell you what, let's defer that to a slide that I have on certification organizations. The answer is no, it doesn't assure reliability or safety of a product, and I'll explain why.
Sure, and what can you do to anticipate failure?
Well, certainly the system reliability model would flag you that there's an issue with the system that could result in a failure. Going through the manufacturing process and procedures that have been executed on the product would certainly flag any issues if there are any. General quality problems with the product. If you see a product that has minor quality problems throughout that were missed during inspection, it may be that that inspection process and manufacturing process wasn't adequate, and they could have missed something major that could result in a future failure.
Okay, those are all the questions we have.
Safety hazard.
So please continue with the presentation.
Okay. Okay, so I wanted to talk about mean time between failures. It's a common metric that's published with products, and the acronym is MTBF. It's a misleading and a frequently misunderstood term. And, you know, I often see that hard drives for computers, as one example, often come with an MTBF label of 1 million hours, and you can look at that and say, wow, that's pretty impressive. I won't ever see a failure with this hard drive. Well, that's far from the truth. So if we go through the mathematics, MTBF is equal to 1 over the failure rate, lambda, and conversely, lambda is equal to 1 over MTBF. So if we take the case where lambda is equal to 1/1,000,000th of a failure per hour, take the reciprocal, MTBF would be 1,000,000 hours. And then if we plug that into the reliability formula, which is equal to e to the minus lambda t, substitute in the reciprocal of lambda, which is MTBF, and perform the calculations, we end up with e to the minus 1, which is 1 over 2.71828, or 0.37, and that says that there's a 37% chance of that hard drive or whatever the product is reaching 1,000,000 hours without a failure. That's not a very good indicator to me. And so I believe that the reliability metric is a much more meaningful number than MTBF. I don't have any proof of this, but I've always believed that MTBF was developed as a marketing tool. Failure mode effects and criticality analysis is a what-if process. It's performed during the product design, and the design engineers go through and identify the impacts of failures and what the result is. They might say, well, what if this component fails? What happens and what's the impact? What if this component and another component fails? What's the impact? And it frequently flags critical product safety issues that can be identified and corrected in the design process. And again, this is getting into failure analysis, but fishbone diagram. In this case, I've got a hypothetical home appliance that caused a residence fire. And you can see, I think, from the diagram why it's called a fishbone diagram. What you do is put in place, in this case, manufacturing, possible defects, field service call factors that could have affected the result, and supply chain issues that could have created the issue. So if each fishbone diagram, based on the type of failure and the type of equipment that failed, is customized, and the fishbone diagram is customized to that situation. So you enter likely and possible causes from your initial look by category. You perform further investigation and analyses that result in some factors being eliminated, but you usually end up with multiple contributory causes being likely, and that kind of correlates with what I told you earlier on having more than one incorrect operation as a factor in resultant failure. And here's what you end up with in this hypothetical case. The fishbone diagram shows that 4 items have been removed as a result of the investigation, and there are quite a number of remaining factors that did contribute to the actual fire. So I talked about root cause earlier, and that's important. It's I think I mentioned that you frequently find that manufacturers go through a very cursory look at what the problem is that caused the failure and resultant hazard. They don't take the time to do it properly, and it results in an ineffective corrective action. So it's important to identify root cause, and root cause is at the bottom, and this is important, at the bottom of the causal chain. So let's take another hypothetical example. The home appliance exploded due to improper factory assembly, and we find that a production operator made a mistake that caused the incorrect assembly. And we find that the operator was incorrectly trained, and we find that the training material was improper, we might end up with a corrective action, a valid corrective action that the training material needed to be updated. Unfortunately, manufacturers don't always go through that rigor, and just to exemplify in this example, firing the operator or the trainer wouldn't fix the problem here. The training material would still be defective and could result in future issues down the road. Product certifications. I didn't think I'd cover this slide yet. This will be a more in-depth answer to the question that was asked in the question session, the previous question session. So there are a number of different certifying organizations. UL Underwriters Laboratory is probably one of the most commonly known in the United States. There are others, Conformity European in France. And I believe that product certification to comprehensive standards, which is what they do, improves product safety. There's no question about it. The reason I said no to the question during the question session is that certifications are based on sampled product. And the fact that you pull 3 products and look at them and ensure that they meet the standards that are required and then certify the product does not ensure that rigorous manufacturing and quality measures are used for other products. It doesn't guarantee, therefore, that the products that come off the line are repeatable and meet the standards. Recertification, which has to be done, is dependent on product frequency or production frequency. And so if you're not producing a product when the recertification comes due, UL has to wait until you're producing that product again. And again, I have no objective proof of this, but in looking at certifications of this type, I'm not convinced that the manufacturer doesn't have some input into which samples are pulled. And so there's another possible cause for inconsistency in the actual products that are sold. The Consumer Product Safety Commission, CPSC, it's a United States organization, federal organization. They maintain and enforce very specific standards for child safety and other specific areas. I think I've seen that refrigerators have in the past caused problems, and so I think they have a specific set of standards for refrigerators. But for all products, just about all products, they don't have specific standards. They operate in a reactive mode. In other words, if a fire occurs, they'll look into it and see if what the cause of the fire was. If it's a product, they'll ask the manufacturer to address it. They do provide some good things. They have an online database for product recalls, so you can look up recall information on products by manufacturer and type. They allow consumers and business to report into a database findings of unsafe products or reports of unsafe products. They provide safety-related education as available to manufacturers, which is a good thing. And they author some pretty effective, in my opinion, publications for guidance to manufacturers and product importers. Their actions are governed by the U.S. Consumer Product Safety Act. The CPSC Handbook for Manufacturing Safer Consumer Products is a pretty decent document. It provides defined processes to allow sourcing hazard-free products. It's provided as guidance, not compliance. so that a manufacturer doesn't have to follow any of the content in the manual. It does align with good industry practice, and so any manufacturer that's doing things properly will typically comply with most of the manual. And it provides those manufacturers and importers self-assessment checklists so they can look at the manual and go through the checklist and determine if they're performing their operations properly. So it's a very good reference to determine if a given manufacturer is performing necessary due diligence, or in the case of a litigation, as a reference to determine if they have done due diligence on the product that's at issue. And because it's basically good industry practice, you can use the handbook contents and apply them to non-consumer products as well. And I find it to be an excellent reference during discovery. It allows me to put together a pretty good list of documents that need to be requested to determine if the manufacturer has done due diligence and followed proper guidelines. The handbook topics are largely what I've discussed already. Design reviews during the design phase, documentation and change control is something I haven't discussed, and that's very important in that if you make a change to the product, all the electrical schematics, mechanical diagrams, instructions, and so forth need to be updated quickly so that the people out in the field and distribution chain have the proper instructions to perform their tasks properly. Corrective action we talked about, audits, end user service, and so forth. CPSC recall handbook, it discusses the recall communication that I talked about in detail earlier in the presentation. It identifies what recall documentation should look like, and it calls out proper corrective action methods, which I've discussed in some detail previously. I'm not qualified to pass legal judgment on this, but if you read the Consumer Product Safety Act, manufacturers are required to report known safety-related defects if they're aware of them. Well, if a manufacturer is doing a really poor job and has no idea how a product is produced or what guidelines are followed, they may not be aware of a safety-related defect, which could let them off the hook. I'm not sure about that. Okay, so in summary, I think I've shown you that manufacturers can employ many available tools to preclude equipment hazards. I've never seen a random failure where everything was done properly. And as a result, you'll always find, and I've never found just one shortfall. I've always found multiple errors in processing at some point that caused the failure. And so there are always liable parties. I should point out also that the liability can be on the end user end as well. I mean, if the end user blatantly doesn't follow proper instructions in using the equipment or uses it for the wrong purpose, they can cause the problem or hazard themselves. Bottom line, and this is a little bit of a professional plug, I guess, but if you have a product liability case that's applicable, failure analysis and root cause identification are a sound investment to make, I believe. And here are some references to some of the documentation that I've talked about that you'll see when you get the PDF copy of this presentation. Underwriters Laboratories website is pretty good. They have available their standards, and you can go in and actually look up a manufacturer and see what standards they're qualified to. So all of these are pretty good references, and I think you may find them useful. And we're back to questions. If I didn't answer the certification question adequately, please ask that again.
Okay, and could all the attendees please type the passcode into the Q&A once again? Our first question is, what role does maintenance play in controlling exposure to an electrical hazard?
Well, maintenance, there are two types of maintenance. There's maintenance that's performed to correct an issue. There's preventative maintenance that can be important that is necessary on a scheduled basis to prevent a product failure. So preventative maintenance, if not performed, can result in a failure. And then maintenance of issues that show up is another form of maintenance, but it's very important and certainly can result in a hazard. Maintenance activities for a product that's out in the field would typically be conducted by the field service organization that I showed in the supply and distribution chart.
Our next question is, could you review the MTBF sample calculation one more time on slide 24?
Okay, is there a particular area that you'd like covered, or the whole thing?
I believe that they meant the whole thing.
Okay, so mean time between failure, again, as I indicated, is a misunderstood term. Mean time between failure is equal to 1 over lambda, and I defined lambda earlier. That's the failure rate over a given period of time. So lambda, based on math, is equal to 1 over MTBF as well. If lambda, and I'm just using this as an example for a 1,000,000-hour MTBF, if lambda is equal to 1/1,000,000th the probability that there will be 1/1,000,000th of a failure per hour, which equals 1 failure per 1,000,000 hours, MTBF will be equal to 1,000,000 hours, which is the reciprocal of 0.00001. And so if we go into the reliability formula and replace lambda with 1 over MTBF, which is the exponent becomes to the minus t over m, and perform the calculations, if time is equal to 1,000,000 hours and MTBF is 1,000,000 hours, the equation becomes e to the minus 1, which is 1 over 2.71828, and that again is rounded off. That's equal to 0.37, and so there's a 37% chance of reaching the 1,000,000 hour MTBF on a given product without a failure. Let me know if that answered the question.
Okay, and the next question is, how do you consider a manufacturing certification such as ISO certification as compared to UL or et cetera?
ISO certification 9000, 9001 is again a good thing, but it primarily reviews documentation that shows some form of process and procedure in place that if the manufacturer follows that procedure, they'll produce a good product. ISO doesn't guarantee that the manufacturer is consistently producing product to ISO standards, and some of those standards, in my view, are subjective, and so I would rate them below like a UL certification. But ISO certification is not a bad thing. I don't think it adds a lot to the equation, though. Just my view.
And can you explain ISO 9000?
Can I explain ISO 9000? ISO is a international standard where a team comes in to your facility typically and ensures that you're following the proper procedures. They go through a checklist. They usually have some recommended corrective action, and at some point they agree that you're doing what you're supposed to and make you ISO certified. I'm not sure I totally understood the question, but.
Okay, and is electrical equipment tested in a failure mode?
Taken to,
Bob, we're having trouble hearing you.
What's that?
We're having trouble hearing you, and there's a little bit of feedback as well.
How is it?
Much better.
Okay. So equipment under the right circumstances and right reasons can be taken to the failure mode. As an example, if you say that a piece of equipment is certified to run up to 125 degrees F in that kind of an environment, you might want to take that piece of equipment up to the failure point in temperature and ensure that the failure point where the equipment stops operating properly is considerably higher than 125 degrees F. I'm just using an example. So yes, the answer to the question would be yes.
Okay. Our next question is, can the end user be responsible for a hazard?
Say that again?
Can the end user be responsible for a hazard?
I'm having trouble hearing you now.
What about now? Can you hear me better now?
Yeah, that's fine. Go ahead.
Okay. Can the end user be responsible for a hazard?
Oh, absolutely. As I pointed out at the end of the presentation, if an end user doesn't follow the necessary precautions called out for the equipment and the way it's used, they can cause a hazard. If an end user, as an example to the question that I just answered, if they use it in an environment that it's unsuited for, they can cause a hazard. If they operate the equipment improperly, they can cause a hazard. So with most complex pieces of equipment, there are a set of instructions that go out to the end user that they need to follow. And, along with that, these days particularly, there are quite a number of safety-related instructions that are called out. If they don't follow those, they can certainly cause a hazard.
Okay, we have one more question remaining. Can the design of an electrical system in a building, which is designed such that it provides insufficient power, be the root cause of the failure of fixtures in the building?
Say that question again.
Sure. Can the design of an electrical system in a building, which is designed such that it provides insufficient power, be the root cause of the failure of fixtures in the building?
I'd have to see the exact situation to give an absolute answer to that, but insufficient power under certain circumstances can cause failures and hazards, yes.
Okay, those are all the questions that we have. In addition to being your best source for testifying and consulting experts, TASA also offers e-discovery and forensic solutions, free interactive webinars, cybersecurity services, day-in-the-life videos, and research reports on expert witnesses, such as the Challenge History Report 2.0, the Professional Sanction Search, and the Expert Profile 360. I want to take this opportunity to thank everyone for attending, and most especially Robert Abend for his time and effort in creating this presentation. If you would like to speak with Mr. Abend, or if you would like to speak with a TASA representative regarding an expert witness for a case that you are working on, please contact TASA at 1-800-523-2319. A TASA representative will be following up with you with regard to your feedback on today's presentation. Thank you again and have a great day, everyone. This concludes our program for today.